In 1932, John von Neumann proved that 100% of quantum measurements create a paradox. His mathematical foundations showed that the wave function collapses only when observed, but your own body's atoms obey the same equations, meaning you might be a ghost too. The ghost was the measurement problem. A single particle exists everywhere until the apparatus clicks. Von Neumann stared at his blackboard, realizing his perfect math described a world that couldn't exist. When a quantum system evolves on its own, it follows the Schrödinger equation, a smooth, deterministic wave that spreads out like ripples on a pond. But the moment you measure it, that wave collapses instantly into a single point. Von Neumann called these two processes Process 2 and Process 1. Process 2 was beautiful, continuous, and reversible. Process 1 was ugly, sudden, and irreversible, and no one knew why it happened. The Copenhagen interpretation, first presented by Niels Bohr at a conference in Italy in late summer 1927, and then repeated at the Solvay conference later that year, had a pragmatic answer: don't ask. Bohr argued that the classical measuring apparatus was simply necessary to describe quantum phenomena, and the boundary between the quantum world and the classical world was an indivisible whole. The question of what happened between measurements was, in Bohr's view, meaningless. But von Neumann was not satisfied with a philosophical dodge. He was a mathematician, and he wanted to trace the problem to its logical end, so he did something remarkable. He showed that the boundary between the quantum system and the classical apparatus, what physicists now call the Heisenberg cut, could be pushed arbitrarily far. You could place it between the particle and the detector, or between the detector and the electrical wire, or between the wire and the computer, or between the computer and the retina of the observer's eye, or between the eye and the brain, or between the brain and consciousness itself. The mathematics allowed it, and that led to a deeply uncomfortable conclusion. Either the cut is arbitrary, or consciousness itself is what collapses the wave function. This was not mysticism. It was a direct consequence of von Neumann's formalism. And it set off a debate that has never been resolved. The double-slit experiment is where the problem becomes visceral. Fire a single electron at a barrier with two slits. Do not measure which slit it goes through. The electron behaves like a wave, passing through both slits simultaneously and producing an interference pattern on the screen behind it. It is not a particle moving along a trajectory. It is a probability cloud, a ghost of possibilities. Now place a detector at one of the slits. The moment the detector clicks, the moment you know which path the electron took, the interference pattern vanishes. The electron now behaves like a particle, hitting the screen at a single point. The wave has collapsed. But why? What physical process caused that transition? The detector is made of atoms. The atoms obey quantum mechanics. So why does the detector behave classically? This is the measurement problem, and it is not a minor technical issue. It is the central crisis of quantum mechanics. In 1957, a young physicist named Hugh Everett decided he had had enough of the mystery. In his PhD thesis at Princeton, titled On the Foundations of Quantum Mechanics, he proposed a radical solution. There is no collapse. The wave function never collapses. All possible outcomes of a measurement are real, and they all happen in separate, branching universes. The observer simply experiences one branch. This was the many worlds interpretation, and it was met with silence and rejection. Everett left academia shortly after, disillusioned. But his idea never died. Meanwhile, the Copenhagen interpretation remained the orthodoxy. Bohr and Heisenberg had won the day, but their victory was fragile. The problem of the Heisenberg cut, of the boundary between quantum and classical, was papered over, not solved. And in 1964, John Bell published a theorem that made everything worse. Bell showed that any hidden variable theory that reproduces quantum mechanics must be non-local, meaning that particles separated by vast distances must instantaneously influence each other. This was not a loophole, it was a proof. The universe, at its deepest level, was entangled, but when researchers looked closer, the data revealed something impossible. The apparatus clicked, and the universe split. That was the implication of what Hugh Everett had proposed in his 1957 Princeton thesis. But the physics community was not ready for a multiverse. They were barely ready for the idea that an electron could be in two places at once. So Everett's work was buried, dismissed as science fiction by Bohr's inner circle, and the young physicist left academia to work on nuclear weapons calculations for the Pentagon. He died in 1982, his interpretation largely ignored, but the measurement problem did not go away. It festered, and in 1964, John Bell's theorem had shown that any hidden variable theory reproducing quantum mechanics must be non-local, a devastating constraint. Yet Bell himself had a favorite interpretation, one that had been proposed decades earlier by a French physicist named Louis de Broglie, and later revived by David Bohm. It was called the pilot wave theory, and it offered a completely different picture of what happens when the apparatus clicks. In the pilot wave interpretation, the particle is always a particle. It has a definite position at all times, but it is guided by a quantum wave, a pilot wave, that ripples through space and steers the particle's trajectory. In the double-slit experiment, the particle goes through one slit, but the pilot wave goes through both. The wave interferes with itself, creating the pattern, and the particle is guided to the bright fringes. The detector click does not collapse anything. It simply reveals where the particle already was. The wave never collapses. It just keeps rippling. This was a beautiful, deterministic picture. It restored causality. It made the world feel sane again. But it came with a price. The pilot wave was non-local. It had to be. Bell had proven that any theory reproducing quantum mechanics must allow instantaneous influence across space. In Bohm's version, the wave guiding one particle depended instantly on the positions of all other particles in the universe. Einstein called this spooky action at a distance, and he hated it. But Bohm accepted it. He said the universe was an undivided whole, and non-locality was not a bug. It was the deepest feature of reality. The problem was that the pilot wave theory was not elegant. It required a special, privileged reference frame for the non-local interactions, even though the theory made the same predictions as standard quantum mechanics. Most physicists found it ad hoc, and there was another issue. The pilot wave had no source. It was not generated by the particle. It was a separate entity, a ghost that existed alongside the particle, carrying information about the entire experimental setup. Where did it come from? Bohm never fully answered that question. Meanwhile, a completely different approach was emerging from the ashes of the Copenhagen consensus. In the 1970s and 1980s, a small group of physicists began asking a radical question. What if the wave function is not a physical object at all? What if it is just a tool for calculating probabilities? This was the seed of what would become QBism, quantum Bayesianism, developed by Carlton Caves, Christopher Fuchs, and Rudiger Schack. In their view, the wave function is not a real thing in the world. It is a measure of an observer's personal beliefs about what they will see next. The apparatus click is not a physical collapse. It is the moment an agent updates their expectations. This dissolved the measurement problem entirely. If the wave function is subjective, there is nothing to collapse. The problem was created by mistaking a mathematical tool for a physical reality, but critics argued that QBism was a surrender, that it abandoned the goal of describing reality as it is, independent of observers. And it raised an uncomfortable question. If the wave function is just personal belief, then what is the world made of? QBism had no answer. It was a philosophy of science, not a theory of nature. Then came the experiments of Anton Zeilinger and his group in Vienna. Beginning in the 1990s, they performed increasingly sophisticated tests of quantum entanglement and teleportation. They showed that the act of measurement could be delayed, that the choice of what to measure could be made after the particles had already separated, and that the outcome still depended on that choice. This was the quantum eraser experiment, and it pushed the measurement problem to its breaking point. The apparatus could click, and the particle would behave like a wave or a particle depending on a choice made after the fact. It was as if the past was not fixed until the future decided what it should be. The quantum eraser experiment performed by Zeilinger's group in 1999 did not just challenge our intuitions, it shattered them. Here is what they did. They fired a photon through a double-slit apparatus, but before it reached the screen, they placed a special crystal that created an entangled pair from each photon. One photon went to the screen. The other went to a separate detector that could be used to determine which path the first photon had taken, but crucially, that determination could be made after the first photon had already hit the screen. The results were astonishing. When the experimenters looked at the screen without consulting the path information, they saw an interference pattern, wave behavior. When they did consult the path information, the pattern vanished, particle behavior. But here was the kicker. The decision to check the path information was made after the photon had already arrived. It was as if the photon's past behavior depended on a future choice. The universe did not seem to know whether it was a wave or a particle until someone decided, after the fact, what question to ask. This was not a trick of delayed signals. The entanglement ensured that the information about the path was stored non-locally, spread across two particles that could be kilometers apart. The measurement at the screen and the measurement of the path information were space-like separated, meaning no signal could travel between them fast enough to influence the outcome. And yet, the correlation held. The universe appeared to be retrocausal, or at least a causal, in a way that made Einstein's skin crawl. Zeilinger himself, reflecting on these experiments, said something profound. It is not a question of reality, but of the information we can obtain about reality. This was the pivot. The measurement problem, which had been framed for decades as a problem about physical collapse, was being reframed as a problem about information. The apparatus click was not a physical event that changed the world. It was a moment when an observer's knowledge changed, and because quantum mechanics is fundamentally about correlations between observations, not about hidden realities, the click was simply the boundary between what could be known and what could not. This led directly to the development of QBism in the early 2000s. Christopher Fuchs, a physicist at the University of Massachusetts, Boston, argued that the wave function is not a real thing in the world. It is a tool, a personal Bayesian probability assignment that an agent uses to make predictions about their own future experiences. The wave function does not describe the world. It describes the agent's state of belief about the world. When the apparatus clicks, the agent updates their beliefs. That is all. There is no collapse of a physical wave. There is only a change in what the agent expects to see next. This was a radical departure from every previous interpretation. Copenhagen had treated the wave function as a real physical wave that collapses upon measurement. Many worlds had treated it as a real physical wave that never collapses but branches. Pilot Wave had treated it as a real guiding field. But QBism said, none of these are necessary. The wave function is not physical. It is a piece of mathematics that helps a conscious agent navigate their experience. The measurement problem dissolves because there is no physical process to explain. The click is just the moment the agent learns something new. Critics were immediate and fierce. David Merman, a respected physicist at Cornell, called QBism the most promising approach to making sense of quantum mechanics, but others called it solipsism. QBism's answer was deceptively simple. The world is made of experiences, not particles, not fields, not waves. Experiences. The fundamental ontology of QBism is the stream of conscious experience of each individual agent. The external world is a hypothesis that agents construct to make sense of their experiences. This raised a question that went straight to the heart of physics. Is science about describing reality, or is it about describing what we can predict? The Copenhagen interpretation had already taken a step in this direction by saying that the question of what happens between measurements is meaningless. QBism took the next step. The question of what exists independent of any observer is also meaningless. The only reality we have access to is the reality of our own experience. Everything else, particles, fields, spacetime, the universe itself, is a model we build to organize that experience. But this left a bitter taste for many physicists. The entire project of physics, since Galileo, had been to describe a world that exists independently of us. QBism seemed to abandon that project. It was not a theory of nature. It was a theory of how agents make decisions, and yet it was fully consistent with every experimental result. It made the same predictions as standard quantum mechanics. It just refused to tell a story about what was really happening. Meanwhile, a completely different approach was gaining traction among a small group of physicists who refused to give up on objective reality. They were looking for a physical mechanism that would cause the wave function to collapse, not because an observer looked, but because the system itself reached a threshold. This was the DOC-Penrose model, proposed independently by Lajos DOC in 1987 and Roger Penrose in 1996. Penrose, a Nobel laureate and collaborator of Stephen Hawking, argued that gravity was the missing piece. He proposed that when a quantum superposition reaches a certain size, roughly the scale at which the gravitational self-energy of the two configurations differs by a single quantum of energy, the superposition becomes unstable and collapses spontaneously. No observer required, no consciousness needed, just gravity. Penrose's idea was elegant but speculative. It predicted that superpositions of large objects, like molecules or tiny crystals, would collapse faster than standard quantum mechanics predicted. Experiments were proposed to test this, most notably by Marcus Arndt at the University of Vienna. Arndt's group began firing ever larger molecules through double-slit apparatuses, looking for the point at which interference patterns would disappear due to gravity-induced collapse. In 2019, they demonstrated quantum interference with molecules containing over 2,000 atoms, as published in Nature Physics. The interference patterns were still there, no collapse, no gravity threshold. Penrose's model remained unconfirmed, and so the measurement problem, after nearly a century of debate, remained exactly where it had started, unresolved. The apparatus clicked, the wave collapsed, or did not. The universe branched, or did not. The pilot wave guided, or did not. The agent updated their beliefs or did not. Every interpretation was consistent with the data. Every interpretation had its passionate advocates and its fierce critics, and every interpretation left something deeply unsatisfying at its core. The most shocking part of this story hasn't even begun, because in the early 2020s, a new set of experiments started probing the boundary between quantum and classical in a way that no one had anticipated. They were not testing interpretations, they were testing the very fabric of space-time itself, and the results would force physicists to confront a possibility that even the most radical interpreters had never considered, that the measurement problem was not a problem about quantum mechanics at all. It was a problem about the nature of time. The experiments that followed Zeilinger's quantum eraser did not settle the debate, they deepened it. Because in 2012, a team of physicists at the University of Vienna led by Philip Walther performed a variation of the delayed choice experiment that pushed the logic to its breaking point. They used a quantum system that could switch its behavior mid-experiment, effectively deciding whether to measure wave or particle properties after the photon had already been detected. The result was the same. The past appeared to be rewritten by the future, but this time, the apparatus was not a simple detector. It was a quantum computer, a system that could make the choice in a superposition of both options, and the data showed that the photon behaved as if it knew, in advance, what the quantum computer would decide. This was not retrocausality in the science fiction sense. It was something stranger. The quantum computer's decision was not made in time. It was made in a superposition of times. The measurement problem, which had always been about the moment of collapse, was now about the structure of time itself. If the future could influence the past, then the arrow of time was not fundamental. It was emergent. And the measurement problem was not a problem about particles or waves. It was a problem about causality. Meanwhile, a completely different line of research was converging on the same conclusion from the opposite direction. In 2013, a team of physicists at the University of California, Santa Barbara, led by John Martinis, built the first quantum processor capable of demonstrating a clear violation of the Bell inequality with no detection loophole. The experiment was performed on superconducting qubits, tiny circuits that behave like artificial atoms. The results were unambiguous. The correlations between the qubits could not be explained by any local hidden variable theory. The universe was non-local. But the experiment also revealed something else. The act of measurement was not a passive recording of a pre-existing state. It was an active intervention that created the state being measured. The qubit did not have a definite value until the measurement was complete, and the measurement itself was a physical process that took time. This brought the problem of the Heisenberg cut back into sharp focus. If the measurement is a physical process that takes time, then where exactly does the collapse happen? Is it when the qubit interacts with the readout resonator, or when the resonator sends a signal to the amplifier? Or when the amplifier sends a voltage to the room temperature electronics, or when the electronics display a number on a screen, or when a human being reads that number? The von Neumann chain had never been broken. It had only been pushed further into the machine. In 2016, a team at the University of Rochester, led by physicist Andrew Jordan, performed an experiment that directly addressed this question. They used a weak measurement technique, which allowed them to probe a quantum system without fully collapsing its wave function. They fired photons through a double-slit apparatus and used a weak measurement to detect which path each photon took. But the measurement was so gentle that the interference pattern remained intact. The photons continued to behave like waves, even though their paths were being monitored. This was not supposed to be possible. The standard Copenhagen interpretation said that any measurement of which path information would destroy the interference, but the weak measurement did not destroy it. It only partially revealed the information. The interference pattern became weaker, but it did not vanish. The implications were staggering. The measurement problem was not a binary switch, collapse or no collapse. It was a continuum. The wave function could be partially collapsed, partially known, partially real. The apparatus click was not a single event. It was a process that could be spread out in time and space. And the boundary between quantum and classical was not a sharp line. It was a fuzzy region, a gray zone where the wave function gradually lost its coherence and became a particle. This gray zone became the focus of a new generation of experiments in the 2020s. At the University of Oxford, a team led by physicist Vlatko Vedral began testing the limits of superposition in large molecules. They fired molecules of up to 25,000 atomic mass units through a matter-wave interferometer, looking for the point at which environmental decoherence would destroy the interference. Decoherence is not collapse. It is the process by which a quantum system becomes entangled with its environment, causing the wave function to appear to collapse from the perspective of a local observer. But decoherence does not solve the measurement problem. It only pushes it one step further. The question remains, why does a single observer see a single outcome rather than a superposition of all possible outcomes? Vedral's experiments showed that decoherence was real and measurable. The larger the molecule, the faster it became entangled with stray photons and gas molecules in the chamber. The interference pattern faded, but it did not vanish entirely. Even with 25,000 atoms, the quantum behavior persisted. There was no sharp cutoff, no gravity-induced collapse, no mysterious threshold. The molecules remained quantum until they were measured, and that is when the most radical proposal of all emerged from the chaos. In 2022, a physicist named Jonathan Oppenheim at University College London proposed a new theory called post-quantum classical gravity. His idea was that gravity is fundamentally classical, not quantum, and that the interaction between quantum matter and classical gravity causes a fundamental breakdown of quantum superposition. In his model, the wave function does not collapse because of an observer. It collapses because of gravity. But unlike Penrose's model, which required a specific energy threshold, Oppenheim's model predicted that the collapse was continuous and universal. Every quantum system, no matter how small, experiences a tiny bit of gravitational collapse all the time. The effect is negligible for a single electron, but it grows with the size of the system. For large molecules, it becomes measurable. Oppenheim's theory was controversial. It challenged the assumption that gravity must be quantized, an assumption that has driven theoretical physics for nearly a century. But it had a crucial advantage. It was testable. In 2023, a team at the University of Vienna began designing an experiment to detect the gravitational collapse predicted by Oppenheim's model. The experiment would use a tiny crystal, roughly 100 nanometers in diameter, suspended in a magnetic trap and cooled to near absolute zero. A laser would create a superposition of two distinct locations for the crystal, separated by about 10 nanometers, a distance large enough that the gravitational self-energy difference between the two configurations would be significant. If Oppenheim was right, the superposition would collapse within milliseconds, the crystal settling into one location as gravity measured it. If he was wrong, the superposition would persist for seconds or longer, and the interference pattern from the crystal's center of mass wave function would remain visible. The experiment was still ongoing in 2026. No results had been published. But the stakes could not be higher. If Oppenheim was correct, the measurement problem would be solved by gravity. The apparatus click would be irrelevant. The collapse would happen whether anyone was watching or not. The universe would be self-measuring, self-collapsing, self-realizing, and the role of the observer, the conscious agent that had haunted quantum mechanics since von Neumann, would finally be dethroned. But if Oppenheim was wrong, the measurement problem would remain, and the question would return, sharper than ever: what causes the wave function to collapse? Is it consciousness? Is it information? Is it branching universes? Or is it nothing at all, a pseudo-problem created by our insistence on telling stories about a world that does not conform to our narrative instincts? The answer, in 2026, is unknown. The measurement problem is the open wound at the heart of physics, and every experiment, every theory, every interpretation is an attempt to heal it. But perhaps the wound is not a wound at all. Perhaps it is a window, and what we see through it is not a failure of physics, but a glimpse of a reality that is fundamentally, irreducibly, and beautifully strange.